Okay, so graphing basic functions review. Now, we're going to start with straight lines. And just like I said yesterday, I'm not trying to insult anybody's intelligence. I'm sure a lot of you remember how to graph straight lines. I'm just going to go through it just in case. I mean, it has been a couple years since we've learned this stuff, right? So we're going to take that knowledge off the shelf and dust it off and make sure that we're all good at graphing our straight lines. So this first one, I'm going to hit you with a little bit of vocabulary early. I'm not supposed to tell you this yet, but this first one, f of x equals x, which means that's the same thing as saying y equals x. This is a parent function. This is the parent linear function, straight line. This is the straight line that all other straight lines try to be like. Every other straight line can be described as a transformation of y equals x. So this parent function, y equals x, it doesn't have a y-intercept. And the reason why I know this is because it's written in the format y equals mx plus b, where the plus b right here would be your y-intercept. Well, this y equals x doesn't have anything there, so you can think of it as saying plus 0. You don't have to write that, but that's how we know its y-intercept is 0, because there's not a number there. So what I'm going to do is I'm going to put a dot on y equals 0 right there. And then it's in slope-intercept form, which means that we need to look to our slope to see where our next point is. Our slope is the number that sits in front of x, our m value. Well, there is no number in front of our x, so that number can be assumed to be 1. And actually, better than 1 can be thought of as being 1 over 1, because your slope is your rise over run. Your change in x over, your change in y over your change in x. So what we would do is we would go back to our y-intercept. We would go up 1 because the top of the fraction is positive 1. And then we would go to the right 1 because the bottom of the fraction is positive 1. And where we ended would be our next dot. Now, if you want more dots, you can just follow the same pattern. Up 1, right 1, up 1, right 1, up 1, right 1, so on and so forth. And then again, down 1, left 1, down 1, left 1. And then we just connect our straight dot, or connect our dots with a straight line. And I'm going to do my best, or I might just cheat and use a straight line tool. I think I'll just cheat and use a straight line tool. There we go. Some students have a habit of not drawing the line all the way to the edges of the graph. They like to just draw something small with arrows on it. Please don't do that, because it's going to make seeing transformations more difficult. So we want to make sure, I completely forgot to change the camera. We want to make sure that we are always, there we go. We want to make sure that we're always drawing our lines to the edges, because like I said, this chapter is about transformations. We want to be able to see transformations. We want to be able to describe transformations. So we want to make sure that our lines go as far as they're supposed to. Everybody cool with the parent function y equals x? F of x equals x? Yeah? Nods? Nobody's freaking out? Okay. We'll move on to the next one. It is still in y equals mx plus b format. And the number at the end, plus or minus, whatever that number is, that's where we cross our y-axis. So for this one, we're going to be crossing at y equals 3. Like that. Now, in the first one, I told you that the number in front of x needs to be thought of as a fraction. Every number is a fraction. Even -2, it's a fraction. There's not a number written underneath it, so it is assumed that the number underneath that -2, is a 1. So it tells us that our rise over run, our rise is actually a negative number. So that would be down 2. So we would go back to our y-intercept. We would go down 2, and then we would look to the number on the bottom of the fraction, which is positive 1, which is to the right 1. So we would put a nice big dot right there. And I use big dots because it hides mistakes. So we went down 2, right 1. We can repeat down 2, right 1, down 2, right 1, so on and so forth. Or from your y-intercept, you could have gone up 2, left 1. It doesn't matter. They're all going to be on the same straight line. I'm going to cheat again, use my straight line tool. Like that. See, fat dots hide mistakes. That line wasn't perfect, but make the dots fat enough, you'd never know. Everybody cool with straight lines? Not too bad, right? Remembering how to do it now? So how about ones whose slopes are actual fractions? It doesn't change the pattern. The number at the end is going to be your y-intercept. So this one crosses our y-axis at +1. Now our slope this time is an actual fraction, but it says -1/2. So the question is, which number is negative, the top or the bottom? Anybody know? Which name? Catherine, which one is it? It's not both, but you're onto something here. But let me describe to you why it's not both. If both numbers are negative, when you divide two negatives, or when you multiply two negatives, what's your result? A positive. So there wouldn't be a point in having the negative sign there if it was on the top and the bottom, because then it wouldn't exist. It'd be a positive. But that's why I asked, because I find that when it is written like this negative sign in front of the fraction, as opposed to the second example where I made sure the negative sign was on the top, I find that when you stick it on the front, students will often think that it goes to the top and the bottom. It's a very common thought. No, the real answer is it doesn't matter. You pick one. Put it on the top or put it on the bottom. Just don't put it on both. It doesn't matter. So you pick one, whichever one you're more comfortable with, top or bottom, and then stick with it. I like to say it's the top number. It's just easiest for me. Now, you don't have to do that if you don't want to. I just think it makes life easy. So I'm going to treat it like that. So I will go to my y-intercept of +1 right here, and I will be going down 1 because it's -1, and then I'll be going to the right 2 because the number on the bottom of the fraction is positive, like that. And then I will repeat the pattern. Down 1, right 2. Down 1, right 2. And then, once again, cheat, straight line tool. Good enough. Like that. Yes, what's your name? Tawny, what can I do for you? Absolutely. So the last one, what I'd like for you guys, if you haven't already done so, is to go ahead and do that last one real quick. And I will confirm your thoughts on this last question because I'm assuming that we're all going to get it right. Just give me a moment if you haven't already done so. Now this one's a little bit easier than the last one, to be honest with you, because our fraction's positive. So we would treat the top as a rise, going up, and the bottom as a run, going to the right, both positive numbers. We're going to cross our y-axis at -2. And then our slope is +3/2. That's up 3. 1, 2, 3, to the right 2, 1, 2. And that is where our next big dot will be. So up 3, 1, 2, 3, right 2. And from there, I'll just cheat and use my straight line tool to the best of my abilities. Somewhere over here like that. Now, you don't need yours to go off the grid like I did. It just made it easy for me to use my tool. And there it is. Thumbs up if we're all there. All right, cool. Thumbs up, my Zoomers. Everybody's good? Okay, cool. Then we will move on to something that's probably not as fresh in our minds. The absolute value functions. Now these things are V-shaped. And the way we can remember that is value starts with a V. It is a V-shaped graph. Okay. These V's either point up or they point down. So either like this or like this. But they are always V-shaped, not curved. The first one, f of x equals the absolute value of x, which could also be thought of as saying y equals the absolute value of x, because f of x is just a fancy way of saying the y values. This is the parent absolute value function. And I don't have a whole lot of space, so I'll say the abs val, parent absolute value function. Now, just like the linear parent function, this one does go through the point 0, 0. See, the dirty little secret is that almost all parent functions go through the point 0, 0. And all the ones that we're going to talk about today do go through the point 0, 0. So the linear went through 0, 0. The absolute value goes through 0, 0. The parent straight line function, the parent linear function, the next point we found it by going up 1, right 1. Its coordinates were 1, 1. So that was here for the straight line. It's also there for the V-shaped graph. Almost every parent function goes through the point 1, 1. It's just something that happens. Now, V's are symmetric. So if there's a point on the right side, there's a point on the left side. So I'm going to take this blue dot that's right here, and I'll reflect it over here, and I will connect my dots, and that's where my V shape comes from. You see, the origin, 0, 0, is what we call the vertex of the absolute value function. So I'm going to go ahead and write that. Vertex. Like that. That is the parent absolute value function, and the point of the absolute value function is called the vertex. Parent straight line goes through 0, 0 and 1, 1. Parent absolute value goes through 0, 0 and 1, 1. But then we just bounce it over, we just reflect it over the y-axis, connect our dots. The vertex can be found by telling me what number makes inside the absolute value bars 0, comma, the number to the far right. So when we look at this one right here, what number would I have to plug in for x to make the inside of the bars equal 0? You can say something obvious. It's okay. Oh boy. What would I need to plug in right here to get a 0 in there? Yeah, 0. You can say something obvious. 0. If you plug in a 0 for x, the inside of those bars is now 0. So I want to identify my vertex. We know it's at 0, comma, and the y value of that vertex is found by telling me what number has been added or subtracted at the end. There's nothing there. So its vertex is also at 0, 0, just like the parent absolute value function was. Now, yesterday, we reviewed our PEMDAS rules, and the reason why is because in order for you to find the next point, because it's not at 1, 1 anymore, in order for you to find the next point, you want to plug in another x value that's really easy to plug in. So after plugging in x equals 0, what would be the next easiest number to plug in? 1. So why don't we just go ahead and plug in x equals 1? So basically, it's like you're making a point tree. Don't know if that's what your teachers called them in the past, but you're basically making one of these deals. The graph is centered at 0, 0, its vertex. It's symmetric around it. We're going to plug in x equals 1, and we're going to see what we get, which is why I had us practicing PEMDAS. So what we have is, and I'm going to run out of space, my apologies, see y equals -2 times the absolute value of 1. But what's the absolute value of 1? Yeah, it's just 1. You see, what absolute values do is they just change numbers positive. And if they're already positive, they just keep them positive. So what this actually says is -2 times 1, which is just -2. So our next coordinate was at 1, comma, -2. That's right here. And whatever happens on the right side of an absolute value graph happens on the left side of the absolute value graph. So we just take the point we just found and we can reflect it over the y-axis. We don't have to plug in -1. We automatically know that this point will reflect to over here. See, absolute value graphs are symmetric, which makes their tables symmetric. They center around their vertex. So I told you the last success criteria was actually noticing how the parent function has been transformed. So I hope that it's obvious that the parent function right here has been flipped upside down, and it appears to be not as wide as it used to be, right? You can see that? For now, I just need you to be able to see it, that it's upside down and it's not as wide as the parent function. When I say not as wide, I need to be doing air quotes, not as wide. That's good enough for now to describe it that way. Is everybody good with this idea? You can see that. Okay. I would also like you to start thinking about, I wonder what made it upside down. I wonder what made it look not as wide. I just want you having these thoughts for now. All right. Let's make our point tree. And the vertex always needs to go in the middle of the point tree. So the question is, again, what number would I need to plug in for x to get a 0 inside the absolute value bars? 0 again, because all there is an x in there. So you would need to plug in 0. I'm putting a v next to it because it's my vertex. You would need to plug in a 0 to get a 0 in there. And what number has been added or subtracted to the far right? You guys can say it. To the far right. A 1, right here. That's always going to be the y value of the vertex. So the vertex can always be found by asking yourself, what would make the inside be 0, comma, what number has been added or subtracted to the far right? That is always how you find the vertex of an absolute value graph. So let's plot that thing. It's at 0, 1. That is here. We now need to figure out a point on the left of that and a point on the right of that. And it actually doesn't matter which way you go. It's completely up to you. What would be the easiest x for us to plug in here? I don't think 8 would be the easiest. We could if you wanted to, but it wouldn't fit on my graph. What would be the easiest one to plug in? 2 would work, or even easier would be 0. So here's the thing. 2 is to the right. Or excuse me, I wrote 2 would be to the right of, what did I do? I plotted this thing wrong. No one's going to say anything? I plotted that wrong. That was 1, 0, not 0, 1. Sorry about that, guys. 0, 1 is here. Might be. Yikes. That was all kinds of confusing. You should have said something. I told you I make mistakes. You should have said something. Don't be afraid to correct me. No big deal. You know how often I'm wrong? My wife tells me all the time. It is not a big deal, okay? According to her, I'm never right. So we want to plug in a number to the right of this, and we want to plug in a number to the left of this, as I was saying before. The number to the right of this dot would be x equals 1. The number to the left of this dot would be x equals -1. And it actually doesn't matter which one you plug in because absolute value graphs are symmetric. So we can plug in either one we want, and I feel like plugging in 1 would be the easiest. So what we're going to get is, I'm going to run out of space, so I'll do it like this. So I'll say y equals the absolute value of, let's plug in x equals 1, and then plus 1. Well, the absolute value of 1 is the same thing it was over there. It's just 1. And 1 plus 1 is 2. So we now have a coordinate at 1, 2. And let's see if I can plot the points correct this time. 1, 2 is right here. So because we found the vertex first, our point tree has to be symmetric. So if there's a 1, 2 down here, then there's a -1, 2 up here, which puts you right there. You see, you only have to find one side of the tree. The other side is a mirror image, and you just connect your dots. So what I would, yes sir, what's your name? Or you could start on the left and mirror it to the right. Yes, absolutely. But what's your name? What? Kevin. You guys said at the same time, confused me. But yeah, so that's what it is. You pick a side. It doesn't matter. Pick the left side, find a point, mirror it to the right. Pick a point on the right side, get it, mirror it to the left. It won't matter. You can plug in any number you like, yeah, but I would, for now, but I would stick to numbers that are on the graph. So 8 wouldn't really want to be plugged in. But so far, you've seen any number work. And the reason why is because there wasn't a fraction on the front. And that's why the last example has a fraction on the front, to show you there is actually a rule for which numbers you should be choosing. If there's no fraction on the front, I'm hoping you've seen by now that the pattern is I just scooted to the right by 1. When there was no fraction on the front, I just went 1 to the right or 1 to the left. It didn't matter. But there is actually a rule for it. These guys are old school passing notes back there. Man, I haven't seen that in a long time. All right, so what I wanted, remember, the last success criteria is just to see how it's different from the parent function. Just to see that this absolute value of x plus 1 looks just like the parent function, except it's been moved up 1. For right now, I'm just hoping you can see that. I haven't changed how wide it is, quote unquote. All I've done is moved it up 1, and I'd like you to be thinking about, I wonder what part of that equation moved it up 1. Just thinking about it for now. And then the last absolute value function does have a fraction on the front. Let's make our point tree. X, Y. We're going to start with our vertex. We're going to put it right in the middle. So this time, what number would I have to plug in right here so that the inside of these absolute value bars equals 0? If I plug in 0, I'm going to have to say 0 minus 1. Is that 0? No, it's not. So what would I have to plug in to get a 0 in there? Livy? A 1. Basically, you just look at whatever's here and switch the sign. Because it says x minus 1, you would have to plug in a positive 1 to get a 0, because 1 minus 1 is 0. So our vertex is at 1 comma, and what number has been added or subtracted to the far right? Is there a number written to the far right? No, I mean all the way to the right, outside of the bars. No, there's no number there. So it's 0. There's no number out there, so you think of it as a plus 0. If there was a number out there like this one, that would have been the y value of the vertex. But there's not, so it's automatically a 0. So let's see if I can plot this one correctly. This one is at 1 comma 0, which is here. There. Now, I don't know about you, but I don't like to have to plot decimals. It really bothers me, plotting decimals. Uh-oh. Is this, what period is this? Second period? Okay, good. I haven't messed up yet. I thought it was third period. I was going to say I forgot to do the 5-day count. Anyway, I don't know about you, but I don't like to plot decimals. And that fraction on the front, it could create decimals. So I need to be careful about what number I plug in. For example, if I just scoot 1 to the right, like I've done in the other 3 examples, the number to the right is a 2. And if I plug in a 2, here's what's going to happen. I'm going to get the absolute value of 2 minus 1. Well, that's 1. The absolute value of 1 is 1. And then I'm going to have to multiply that 1 by 1/2. Oh, shucks, a decimal. So moving to the right one created a decimal. I don't want to do that. So just educated guesses. How far to the right do you think I should move? 2. Yeah. If you move to the right 2, which puts you at x equals 3, you won't get a decimal. So how did I know to go plus 2 right here? How did I know to do that? It's the number on the bottom of the fraction. The number on the bottom of the fraction tells you how far to move to avoid plotting a decimal. So if that was a 1/3, I would have gone to the right 3 points. So we have to plug in x equals 3, and we won't get a decimal again, I'm out of space, so I'll just do like this. And we're going to say y equals 1/2 times the absolute value of. The x we're going to plug in is 3. So it says 3 minus 1 plus 0. I don't need to write plus 0. Well, 3 minus 1 is 2. And since 2 is already a positive number, the absolute value doesn't do anything to it. So it's just 1/2 times 2, and 1/2 times 2 is 1. Look, no decimal. So that point is going to be at 3, 1. And if I went plus 2 this way, then it's symmetric. You go minus 2 the other way. Or you could just look right here and go, all right, from my vertex, I went 1, 2 to the right, so I need to go 1, 2 to the left. And the great thing about the tables is the y values are symmetric as well. So no work is required for me to know that that is a 1 right there. If that concept isn't making absolute sense to you, pun, absolute values, absolute sense. If it's not making perfect sense to you, please say something. Let me help. I'm going to connect my dots at -1, 1. And again, the last success criteria is just for now thinking about how this one is different from the parent function at the top left. What I'd like for you to be able to see is that it has been scooted to the right by 1. And I'd like for you to be thinking, I wonder what part of the equation moved it to the right by 1. I'd also like you to see that this one looks, and I'm going to use the air quotes, this one looks wider than the parent function. And I'd like you thinking, I wonder what part of this made it look wider. That is the 4th success criteria. In the upcoming days, we will be really specific about what is causing these things to happen. But now I just want you thinking and predicting. We good on absolute values? Yes? Yes, sir. What's your name? Nick. Well, it does. So he wants to know when we plugged in 3, what happened. So right here, I've plugged in 3, and that's why I switched it to red. That way you can see that that was me plugging in the 3. But I have to use order of operations, and that starts with P for PEMDAS. I mean, for parentheses, right? You treat the absolute value bars as a set of parentheses. So you handle what's inside of them first. So then you do this 3 minus 1 first, which is where the 2 is coming from. That's right here. And then you have to do the absolute value because, again, you're treating them as parentheses, so your job is to have those bars do their job. And the absolute value of 2 is still 2, and that's why it's just in parentheses right now, and then we do multiplication last. Okay? See, and this is a good question, and this is why I spent time going over PEMDAS yesterday, because you are going to have to be able to plug numbers in to build your point trees. And I'm trying to make that as quick as possible for you. Okay. Any other questions? That's what we're here for. People at home? Remember, all you have to do is hot mic and start saying something, and I'll listen. Okay. Well, then I'm going to clear it, and we will go to our quadratic functions. These are U-shaped. But I have some really good news for you. All the rules that we just learned about absolute value functions, how do you find their vertex, and how do you move to find the next x values, symmetry, all of those things are also true for quadratic functions. They're all still true. The only thing that changed is the shape of the graph. So while absolute values are V-shaped, quadratics are U-shaped. That's the only difference. All the rules still apply. When you draw your quadratic graphs, please make them curves, not sharp points. Once again, this is the parent function. So this is the parent quadratic function. All U-shaped graphs will look like a version of this one. They'll be moved around, flips upside down, reflected places, stretched and shrink, up and down or left and right. But they will all be a version of this parent function. Just like the straight line, Just like the V shape, this one is centered at 0, 0. Just like the straight line, just like the V-shaped graph, this one goes through the point 1, 1. If you're not sure why, you could always plug in x equals 1. And when you plug in x equals 1 right here, you get 1 squared, which is still 1. Just like the straight line, just like the absolute value graph, this one's also symmetric around its center. So if there was a point 1 to the right of the y-axis, there will be 1 to the left of the y-axis. And those 3 dots are enough for you to get away with drawing this thing, because it's a sketch. It's not a perfect graph. It's a sketch of a graph. All you have to do is make sure it's U-shaped. And the fatter your dots, the harder it will be to see your mistakes on connecting them. So this is going to be really, really similar to the absolute value graphs. But instead of having the straight up and down bars now, we have the exponent of 2. So I want you thinking that the thing with the exponent is your quote-unquote inside. I want you thinking about it looking like this. You don't have to do that. You don't have to draw them. I want you thinking about it like that. The thing with the exponent is considered my inside. Imagine there was parentheses around it. So for this next one, I am going to draw them just to drive home the idea. The negative 2 does not have an exponent. Only the x does. So those parentheses would have been here, like that. The negative 2 does not have an exponent. And just like the absolute value graph, that point in the center is called the vertex. So when we build our point tree, our vertex will still be in the middle, and the rules for finding it are still the same. What number would I have to put inside those imaginary parentheses so that there was a 0 inside those parentheses? You could say it. Lots of people could say it. I'll ask again. What number could I put inside these imaginary parentheses so that there was a 0 in there? 0, yeah. I know. You can plug in a 0. To find the y value of that vertex, you're going to look to the far right. What number is added or subtracted to the far right? Well, is there a number over there? No. So what is that number then? It's a 0. You think of it as being a plus 0 over there. So your vertex is still at 0, 0. Just like the absolute value graph, you look to the number in front. If there is a fraction on the front, that is going to control how far you move to get no decimals. But negative 2, the way it sits, is not a fraction. So since it's not a fraction, I can just instantly go 1 to the right, because that's easy to do. You want to try to stay close to your vertex whenever you can. So could I plug in x equals 8? Of course I could. 2 problems, though. That's really far away from the vertex, and also that is off my graph. But the point is I could. You want to try to stay close. So since that negative 2 is not written as a fraction, we will move to the right 1. So the next x value I want to look at is x equals 1. And then we have to plug in x equals 1, follow PEMDAS, the order of operations, to figure out what y is. I'm at a space, so I'll come down here. Y is negative 2 parentheses 1 squared. Our order of operations says parentheses first. Well, that just means could you do something inside the parentheses? No, I can't. It's just a number in there. The next letter in PEMDAS is E, exponents. So now I do the exponents. I have to handle 1 squared. That just means 1 times itself. It's just 1 times 1, which is still 1. And the last thing I could do is my multiplication, which is going to give me a negative 2. So I can plot the point 1 comma negative 2. That is right here. So if I was able to move to the right one, I'm able to move to the left one in the other direction. And the table has to be symmetric. So if this y value down here is a -2, this y value up here is also a -2. And you can connect your dots. You just make sure it's not pointy. Just make sure it's curvy. Like that. So that's really the only rule that changed. You have to be able to follow PEMDAS, and it's curvy, not pointy. That's it. It's exactly the same as an absolute value graph, except for it's curvy, not pointy, and you have to follow the order of operations. At least those are the rules. The rules are pretty much the same. I would like for you to be able to see success criteria number 4, be able to see how it's different from the parent function, be able to see that it's upside down, and be able to see that it appears to be skinnier. And I'm saying appears to be on purpose. Because yes, it does look that way. Okay? And it's okay to say that for now. Time is this period over? 14? Lots of time. All right, cool. This one. There are no parentheses, but we pretend there are, like that. I could draw better parentheses. There we go. Going to draw our point tree, and just like last time, the question is, what would I need to plug inside? What would I need to plug into those parentheses so that there's a 0 inside the parentheses? It's obvious. Shout it out. Shout it would be like lots of people. 0, thank you, 1 or 2 people. My goodness, guys, it's going to be a boring year for you if you don't interact with me. I can shut down too. So let's plug in a 0. Oh, and we don't need to plug it in. We could just say what numbers added or subtracted to the far right. A 1. All right, so your vertex is at 0, 1. I'll plot 0, 1 correct this time. There. There is not a fraction in front of those parentheses. That means it is safe to move to the right a unit of 1. Boink. Or to the left a unit of 1. It's up to you. It doesn't matter which way you go. You're going to get the same y value because these things are symmetric. Plugging in +1 is very easy to do, though. So let's plug it in. Y equals set of parentheses, and I'm plugging in x equals 1, and that's why I changed the color, so you can see that that's what I plugged in. Order of operations says I'm going to have to handle the exponents first here because there is nothing to do inside the parentheses. 1 squared means 1 times itself. 1 times 1 is 1. So I have 1 plus 1, which ends up being 2. So if there's a 2 down there, there's also a 2 up here. We plot our points, and we connect them with a curve. So again, I'm asking you to see that this looks like the parent function that's just been moved up 1. And I'd like for you to be asking yourself, I wonder what made it move up 1. And we'll move on to the last example. This time there's stuff inside the parentheses. So plugging in 0 won't get me 0 inside the parentheses. I need the inside of the parentheses to equal 0. So what x value would I have to plug in so that the inside of the parentheses equals 0? -1. Once again, it's the opposite of what I see inside of there, -1. Because -1 plus 1, -1 plus 1 would have given me 0. And what number has been added or subtracted to the far right, meaning outside of the parentheses? 0. There's nothing there. So, yeah, my vertex for this one's at -1, 0. And then for this one, yeah, there is a fraction on the front. So the rule still works. You look at the bottom of the fraction. You see that it's a 2. That means if you don't want to graph decimals, move to the right 2 or to the left 2. So if I move to the right 2, I get x equals 1. If I move to the left 2, I get x equals -3. And you plug in either one of them, it doesn't matter which one, because the graph is symmetric, you will get the same y value. I think plugging in 1 is easier. So I'm going to plug in 1. Y equals 1/2, parentheses, something plus 1 squared. I'm plugging in x equals 1 here. and we follow the order of operations. PEMDAS starts with P. Means clean up the inside of the parentheses if you can, and this time I can. There's something to do. I can add the 2 ones inside the parentheses. There's a lot of 2's right there. The order of operations after parentheses says E, exponents. You can now handle the exponent. 2 squared means 2 times itself. 2 times 2 is 4. So I now have 1/2 of 4. And then you just multiply. Half of 4 is 2. So that means this y value is a 2, and so is this one. Plot them. 1, 2, and -3, 2. Connect your dots with a U shape. And again, I'd like you to be thinking about how this one was different from the parent function. I'm hoping you can see that we have scooted it to the left, and it does appear to be wider than the parent function. And if you can see those things, I am thrilled. And I think that is all we have time for today.